Okay, the last speaker this afternoon is Michael Benedict from Royal Institute of Technology in Sweden. He talked about coexistence phenomena in two-dimensional maps. Thank you.
Hello. Yeah. So it's a great pleasure to be here. I've been here quite a few times, and the first I don't quite remember. Maybe you can help me, Marcella. It could be in the late 80s, 89. Yeah. So then. Yeah, exactly. So. Then we met, and I will speak about this work with Carlson and Marcelo and Leonardo Mora took it up. I will speak about that. It was starting point of this talk also. So it's a really great pleasure to be back after all these years. And we have met. So I will mention two joint papers in this series. So let me start with attractors, and there are basically three definitions of attractors. There is a topological definition by Conley. So you have a trapping region, so that the image of you mapped into self, and you can take the closure, it's contained in you. And then you could form the forward images either with or without the closure. It doesn't matter really. Sorry. And then there is the definition of Milnor of an attractor, a measure theoretical attractor in the sense of Milnor in his well-known paper in Communications of Math Physics. And that is sort of a measure theoretical attractor. It's sort of a statistic of a dynamical system. And then you take the Birkhoff averages of FJ applied to, it should be minus, it should be, well, it doesn't really matter so much, but it's independent of the notation. It converges to the integral of a test function phi with respect to the measure. And so, and there should be a positive Lebesgue measure set of points, so that this is sort of a physical measure then in the sense of Milnor. There is a third definition of attractor due to Ruel, which I wanted, but it's definitely using chain recurrent sets and so on. But I don't know if that has been used so much. But it's an interesting definition also. And then we have a SRB measure for Sinai-Ruan-Bowen. And those are measures which can decompose to have some index set. The coordinates are alpha, and then you integrate with respect to a measure on alpha, and the mu alpha have absolutely continuous conditional measures. The conditional is really this definition. And then actually, if you have an SRB measure in this sense, under suitable conditions, it is a physical measure, and this is due to Pearson. But there are other physical measures, sinc measures, Sandman point measures along an attractive periodic orbit. And somehow what this will be about is the dichotomy between this situation. You have the absolutely conditional measure along unstable manifold, or the sinc measures. And there is sort of famous conjecture by Jacob Pallis, and he conjectured that there is sort of, he doesn't give all details, all conditions, but there's a dense set of dynamics. So any element in the dense set have finitely many attractors. And for an attractor, we'll also discuss the union of basins of attraction. It's the backward image of a trapping region. And the attractor should support a physical measure, and in some sense, and this is a little unspecific, but if you have a parameter family, essentially almost all for almost all parameter values, the union of the attractor is equal to the basin, and all these perturbed, all these attractor supports a physical measure. And then what he also expected is stochastic stability of attractor. So if you perturb a little bit, and I mentioned a result in this direction by Marcello and me also, then the invariant measure and the attractor are stochastically stable. So you expect this to be a dichotomy, not always, but with respect to some parameter measure, Lebesgue measure. So, and I think there is essentially only one case where, correct me, Misha, is there another case beyond your theorem where this has or a similar more general UD model maps has been done also, but nothing in higher dimensions. So this is somehow the first theorem of this kind that existed. So in the quadratic family, you can write the parameter sets in this normalization. The parameters between 0 and 2, and they decompose into parameters with an absolutely continuous and parameters with an attractive periodic orbit, and for the parameters in the set B, that parameter set is open and dense, and then there is also work by Swiatek and Gradczyk parallel to Misha's work. And in both cases, the critical orbit, which is in this model case, there is only one critical orbit, is generic for the invariant measure, and this was actually done the first case of some positive measure set of parameters where this thing hold was done by Carlson and me, but Arthur Avila and Gugu Moreira proved this in principle for almost all points in the set A, and they proved also that you have the Collet-Ekman condition. So this is somehow now very well known thing and very fundamental. But and then the density of hyperbolicity, which correspond to the Fatou conjecture, was proved by Kozlowski, Shen, van Strien. But I haven't seen really that the critical points are generic in this sense in this case. So this, as far as I know, this still open. But I mean, this is in this talk. It's I mean, it is what I will say will illustrate this, that a critical point is associated with some sort of physical measure, at least in many cases. In the Miserevich case, this was proven. But of course, there could be the two critical points could be attracted to the same physical measure, though. This is possible.
Can you explain what you mean by genesis
Converges to the absolute continuous motion.
Yeah, this is part 2 in Carlson, and my paper was the first version of that. But then Avila Moreira did it in much more generality with completely different methods. So I will try to say something about police conjectures, some special cases, and the rule of critical points in the Henon family, which I'll define. And that doesn't have critical point, but in some sense there have a substitute of a critical point, and then we'll speak about then coexistence of maps with SRB measures and attractive periodic orbits. So the basic papers are one Carlos and me, and one Marcelo and Leonardo Mora. So let me recall the Henon family can be written in many ways, and for some reason there are reasons to write it differently, but Carlson and I use the original notation of Henon, which may be not the best, but I mean, for you people who weren't present at the time, this computer experiment of Henon was somehow a starting point for this. So I will just mention it. And, most of you already know it, I guess. So Henon took some parameters which happened to be 1.4 and 0.3, and he took an initial point and plotted, say, 100,000 points, and the iterated point they got on a strange attractor, one call it, because it is an attractor. All initial points tended to, except those who went to infinity, tended to go to this strange-looking picture. And what it was very curious, for at least for me and Carlson at the time. So if you enlarge it, you get the same picture, and you can do it more times. So I will omit it. And in this case, one can prove that there is a trapping region, and then you can form this Conley attractor. And the cases which is mostly interesting here is you have an A-B space. So you have A close to 2 and B is 1 up there. So you live here, very, very close to the full quadratic map. And in this case, in the paper Mora and Marcelo, they had a trapping region, but in one of my papers with Marcelo, we did it a little better and more carefully, and so we really proved the trapping region. But so there is something that is attracted to this object, and it is actually this Henon map. What this is it's the unstable manifold. There is a fixed point which I will denote by C hat, and it's in the first quadrant, and the attractor is the unstable manifold that sort of winds around and has this very strange behavior. But still, it could in principle be that you sort of first go to sort of this closure of the unstable manifold, and then you are attracted to maybe a sink on this closure. And this could not, so the attractor could be along attractive periodic orbit, and the opposite direction is the Newhouse phenomena of infinitely many coexisting at attractive periodic orbits. So, and this couldn't be excluded at the time. But then Leonard Collison got interested, and I helped him, and we managed to prove in a parameter region, which I indicated that are positive one-dimensional Lebesgue measure sets of A, B. So, and for all those points, there is a point whose so that the orbit of that point is dense on the unstable manifold, and that critical point, which this will be, in some sense, a critical point in. It should be located here. This is the C naught, and it has a dense orbit on the unstable manifold. So this means that you don't have a long attractive periodic orbit. And then Lai-Hsien Yang got interested in this, and she and I worked out sort of the Sinai-Rel-Bowen theory, and we proved that there is a set in phase space of positive Lebesgue measures. So this is an attractor in the sense of Milnor. So this converges to the SRB measure, to an SRB measure, which has the SRB property, the absolutely continuous condition measures on unstable manifolds. So then Marcello, already when our paper was a preprint, he started to work on he proved actually that the same theorem as Collison and I had can be carried out in a geometrically much more interesting situation. Is these non-like maps which appeared in connection with homoclinic bifurcation, which was pioneered by Palise, Torkans, and Newhouse, I would say. And so there is a renormalization of if you have a homoclinic bifurcation, there is a renormalization of a map, and which is of this non-like form. And so the classical Lennon maps is just a rescaling, so it's just this map. So it's a special case, but this is much more general. And so they carried out basically, well, based on this machinery that Collison and I worked out, but there are many new aspects that appears in the non-like case. And then Marcello and I worked on the basing problem. You know, in Lai-Hsien Yang's and my paper, we proved that there are some positive Lebesgue measure of initial points, so that the Berker average converged to a measure. But we were managed to prove it for almost all Lebesgue, almost all points in the basin. So and then we went on to work on another part of sort of police program in this setting, and we did various types of random perturbations. So you define a Markov chain by iterating with this xenon-like map and adding a noise, which they could be IID random variables or supported on some ball, but we managed to do much general perturbations than that. But for this talk, I will just formulate. It's the first version that we had. So you have a Markov chain, and that has a stationary distribution. And if the variance, the size of a noise tends to 0, it converges to the SRB measure of the non-like map. And it's sort of natural to mention the thesis of one of Marcello's students, Vitor Araujo, who did a very general form of Palise conjecture with noise. I think it is some very nice work. I won't formulate it, but you can understand the spirit. This you can have finitely many natural attractors in this case, which are now they're always smooth because of noise. So what I would should try to say something new, and so Liviana Palmisano is a former student of Jacek Gracuk. Many of you might know her. She wanted to do something on maps. I hadn't done very new things for a long time, and we tried to prove sort of coexistence of parameters so that F has at least k attractive periodic orbits and also a strange attractor in the sense that is it's a SRB measure on the closure of an unstable periodic unstable manifold of a fixed point, no, of a periodic point. And so we didn't know it at the time, but it's sort of well known that using the machinery of Newhouse to create several attractive periodic points, one could do this. But 1985, when Clark Robinson did it, the strange attractors didn't exist, but he could prove in one parameter families coexistence of different attractive periodic orbits, and he could also prove a Newhouse phenomena in one-dimensional family. So we didn't know it, but we should have known. But it was a little before my time, actually, in dynamics. And what the methods also give, Liviana's and my methods give that the Newhouse phenomena occurs that there are infinitely many coexisting attractive periodic orbits. And it's sort of a more constructive way to do the Newhouse stuff, but it's not, we don't get sort of such a big set of parameters as they do. They use bare category and so on, but what we did is completely constructive somehow. It's inductively proceeding with the thing. And sort of, but since, I mean, using Robinson and a little more, where you could actually do the coexistence. So perhaps the main result in this paper which is in a preprint form now, is that there is a parameters of positive. This is the classical non-maps again. There are parameters for which the non-map has two coexisting strange attractors, and but we can say nothing about the basin. It's sort of in this. We don't have at all the machinery that Marcello and I developed. So it would be, of course, interesting to do something in that, but I don't know much in this direction yet. And let me tell you about a computer study by James Carey from 1979. It's not such a well-known paper, but it was, at that time, these computer experiments were fancy, and he did something following up Henon's original computer experiment. And this picture is somehow, he uses still b equal to 0.3 because the pictures are nice, but he varied parameters. And you could see that what appears is somehow, depending on the initial point, there are this strange attractor here and this strange attractor here. This was observed really, just a computer experiment, but this coexistence phenomena was observed experimentally then. And let me just review some of it's not complete at all, I guess. This coexistent result. First is the famous paper of Newhouse, and one paper is by Raoul Urus, and is the SRB measure for the good parameters. You can weakly approximate it by a measure given by point masses at the periodic orbit. And then there is a paper by Colley, Edward Colley, which was a student of Palise, and there were papers by Pomerina and Rodriguez about coexistence and persistence of strange attractors, and Pierre Berger proved that in the Henon family there is maps with one attractive periodic orbit and a strange attractor. And he also managed to get results about the basin. So one could be very bold and state a version of Palise's conjecture for Henon maps, and I pose it as a question: are there, at least for almost all the big, only most finitely many things and strange attractors, and maybe you can do something with the basin, like Marcello and I managed to do in the most classical cases. But you could then there are many questions of this type which are sort of technology isn't appropriate yet for. So let me say a little bit about the ideas of a proof. And in some sense, the one-dimensional case, it was this first paper by Collison and me where we sort of reproved Jacobson's theorem in which is existence of absolutely continuous invariant measures. And we proved, which would now be called a Collet-Ekman condition with sub-exponential growth. And then you could independently prove an existence of absolutely continuous invariant measure, but you can also use a condition by Nowitzki and van Strien that this sum is convergent, and this proves existence. This proves Jacobson's result then. And let me. It's almost. This is a bit ridiculous to be able to say anything. I think I was to say something about the proof in the one-dimensional case. So you have this psi j is the orbit of a critical value, and then you do a parameter exclusion, essentially because parameters get close to a critical point where there is loss of derivative, and there is a sort of more analytic than dynamic partition of a return interval, and then there are sort of starting things. It's free returns, which means that the image of a parameters covers a certain interval of this type IRL, which is sensory exponential, and there is this very important notion of bound period, which means that a returning point follows the critical point, and that it's a different condition than the approach rate. And somehow the reason why all this works in some sense is the derivative compensation, that if you have a free return n and then you have a derivative, and if you do a computation, you see it's dn times dnp, and this is I mean, you see here is the sub-exponential thing, and sorry, but we sort of carried out the same stuff than in the non-case, but in this case, you really, for various reasons, you must have exponential growth. So this implies a large deviation argument, that you cannot, the frequency of returns to a small interval is not so high, and they are not so deep. So there are lots of estimates here, which I cannot go into here. But an important thing is an escape situation. And so there is a parameter interval. This is now, we are one dimension. And at some time n, this interval is long, say, of length 1/10. And then after a few iterates, this will iterate and hit zero, and that creates a sink. This is in a paper by Hans Thunberg, a former student of mine, and Marcello was actually the official opponent for the thesis defense, but this was not in his thesis. But this construction, which is sort of similar to what Juris did, is sort of a basis on this work Marcello with Liviana. So this creates a sink, and it's fairly easy to see that it's weakly close to the absolutely continuous invariant measure. So in the non-case, there are critical something called critical point. There are no critical points, but the geometry of is actually what happens is actually we do a parameter selection at the final stage. There is this unstable manifold here, and through it there is a local stable manifold, which is infinitely long. This is what happens in the final construction. So so this is and now that there is no longer only a critical point after the final parameter selection, but there are other critical points which all live on long leaves on this unstable manifold. So and there are other tangency points here. So these are lots of possible critical points. So sorry, I'm bad at this. So this is the idea here. And the infinitely long. This is approximately true than in the inductive construction. So this Collier-Ekman-like condition is replaced by this, or you should work at the critical value instead, which I learned by Marcello. There are advantages to work at a critical value. So this is the so-called Collier-Ekman condition. And then we look at, instead of psi j of omega for some parameter interval, we look at the image of a first approximate critical point, but now applied to instead of one, you apply it to, say, the vertical vectors. And there are, now it's a lot of machinery which is impossible to go into, especially it's hard distortion estimates which were improved in the paper with Marcello's paper with Leonardo Mora. So let me actually show a bit of pictures of the phenomena here. So here is this approximate critical point, and really it comes from a pullback of a stable foliation which exists at a critical value. But you can pull this back to the critical point, and here the approximate stable foliation is essentially vertical, and there is a sort of stable manifold theorem which exists in a region of some finite order. And then it's also important is that there is the stable foliation at the fixed point. And now I'm sorry about but now I try to say a little bit about how you create sinks. So you have a point C naught, which also is sort of approximate critical point, and then its image at some stage you want you look at the region of, say, this type around the C is meaning coordinate along the. It could be C naught instead here. And what you attempt to do is dn is sort of a derivative expansion, is to let it hit into this moon-shaped region like this, and what this picture is really various images of this parabolic thing with different critical points, and they all end up into this moon-shaped region, and then you can see what the derivative of this is. It's really quite big, but it's more or less Jordan box of this type, so it's really contracted after some iterates. So you create the sink, and then what you can do now is you can, because of this picture here, you have actually many critical points, and there is a wealth of critical points, and you could take a point just outside the moon-shaped region, and it won't be trapped then, but it will end up, the image will end up here, and then you can use this binding argument again and get expansion for that secondary critical point, and so the C naught is trapped into a sink, but the secondary critical point will have freedom, and you can do essentially whatever you like with it. In principle, this is some picture of the red is. Red is the locus of a critical point, and so this is a picture that you can create a tangency. There is a subtle thing that the tip is not exactly the tangency, but I will omit that. And then you get into a standard picture of unfolding a homoclinic tangency. This is from the Palise Tokens book, and then you can start to apply the machinery of Marcello and Leonardo Mora at this homoclinic tangency and start to create a strange attractor, and then you can do a new sink and yet another tendency and so on. So you can do K sinks and then stop by doing a strange attractor. So this is a constructive way, and if you just continue, you get Newhouse phenomena. So let me turn to the coexistence of two strange attractors. And this is related actually to the structure of the stable manifold of the fixed points. So there are legs of the stable manifolds all over the place here at these parameter values. So what you can do is sort of try to construct using these two critical points and construct a simultaneous almost tangency. So at the almost tangencies you get Henon-like maps with different parameters. I mean, using the renormalization of Palise Tokens, Moraviana, you get two things like this, and then there are these parameters sets which are both close to the parameter to the full quadratic set, but there are somehow this, and there is the mu and nu parameters, and there is a fairly large fraction of good parameters in many intervals of the type Ij. So if the density is enough, you must get an intersection, and this is it.
Thank you. Any have some question or comments?
Thank you, Michael. So when you say two strange attractors, you mean exactly two, or at least two?
At least two.
At least
And
two.
I forgot to say why there are two. It's really because of one is the tangent, one tangent is here and one is here. So these are both parts of the stable manifold. So they are pretty far apart. So they don't intersect. These attractors are very local, but there could be many more, and that's the problem.
Right. Yes. Okay. Thank you.
You have kind of plenty of critical points floating around. Is
Yes.
there some special critical point which you can characterize intrinsically, and you say that this is the one which is important, and that is one, this map exhibits these unimodal features, unique SRB measure, unique attracted. Is there any chance you can
I
do that?
wish I could say that, but I think each, if they are separated enough, they have each one model. But in some sense, you have all these possible critical points, and some of them don't tend to live their independent life, right?
Even
And they sort of, but it was very important, this thing that C and this other critical point was outside here, and it could still be helped by the first critical points to get expansion. So it's.
I mean, not these later examples, but your original examples with Carlisson, which exhibits features of unimodal maps. So
Then everything is sort of so close to unimodal. And we
Yes,
take
but-
this one critical point, this favorite critical point, which lives here, and that's the one which we prove density, topological transitivity for, and so on.
But so do you think there is a chance to say that this critical point is actually a special one somehow? Is it is
Well,
distinguished one?
I have no idea, to be honest.
Thank you.
As far as I remember, Marcel also wrote a paper about two-dimensional case when you have like one-dimensional, one direction is uniformly hyperbolic, one is non-uniformly hyperbolic. And my question, if you can consider like two-dimensional expansion where both directions are non-uniformly hyperbolic, do you have coexistent phenomena in this kind of setting?
Marcelo should answer this question, I think, because he asked about two expanding directions, and this is still very open, isn't it?
I mean, I didn't think about it, Dima, quite honestly, but I would tend to think that the answer is yes. If you allow me to give an answer by the end of the afternoon without thinking too much about it, I think it's yes.
No, I forgot to mention Marcelo's thesis, also where he has one expanding direction and multiple contracting directions. So this is there is more geometry. I planned to mention this, but I forgot.
Okay, thank you. We thank Michael again.